Hi everyone, and indeed today I will present some work that we did with Jean Fedi and Tom Boken and Stéphanie Alassonia from HECA team about new visualization techniques for vascular trees that are aimed to better encompass the geometry, intrinsic geometry of the blood vessels in the visualization. So before diving a bit more in the mathematical details, I will first say a few words about the context and the clinical applications that we are targeting here. So interventional radiology is a medical specialty where the medical doctor performs some operations in an image-guided way in real time. So this is how a surgery room typically looks like, with a big scanner in the middle of the room that can move in the 3 dimensions of the space. And thanks to this imaging device, the radiologist can basically perform and have some feedback on its operation in order to adjust what he's doing in real time. So this kind of imaged guided intervention can take multiple shapes, but a very common kind of operation consists in navigating in the blood vessels of the patient. So more precisely, the goal is to push, let's say, a drug or a medical device in a very specific location of the body of the patient through the use of a catheter that will be guided through the blood vessels of the patient, and that will be able to reach quite a deep part of the body without needing a heavy surgery. So typically, the radiologist will push a needle in the patient in order to have access to his blood vessels, and will then introduce a catheter in this needle that will be pushed toward its final location. So this can be used for different kind of applications. It can be used in order to change the local fluidity of the blood in order to make the blood coagulate and stop an hemorrhage, or on the opposite, to help dissolve some kind of clots in the blood vessels. It can be used as a way of killing tumors by releasing, let's say, microwave or cold gases in a very specific area of the patient. Or finally, can be used to repair aneurysm or to consolidate the blood vessels and restore the original blood flow by pushing some stents that are kind of metallic grid structures that will be introduced in a targeted location with this catheter, and then a small balloon will inflate the structure and make it, giving it its final shape. So all these applications have been made possible thanks to the availability of high quality and real-time imaging techniques that helps the surgeon to know where its catheter is exactly, and help adjust its trajectory. So in practice, the doctor will be able to change the orientation and the direction of the catheter by just applying a rotation, a torsion of the catheter at its extremity that will be transmitted through the whole cable, and that will change the orientation of the head of the catheter. And by doing so, he will be able to change the orientation of the catheter, hence giving it the possibility to choose which blood vessel to follow, especially in junctions. And so this is how he's able to guide and to control the trajectory of the catheter.
Yes, because something that is not obvious on the pictures that you made is that the catheter does not end with a straight head, but like there's an angle. So basically, if you apply torque on the wire, then the angle part of the catheter is going to rotate, and then it allows you to choose the precise path. And then they really have an arsenal of catheter tips that they may be able to choose from. Like some of them make U-turns, etc. It's quite different.
Yeah. So yeah, basically, the point here is notably that the choice of the kind of catheter and the shape of the head is really guided by the geometry of the vessels that the radiologists will have to follow. And so depending on the structure of the vascular system he's working with, he will have to choose different kind of head for the catheter and different kind of materials that will be more or less rigid in order to be more suited to the, let's say, the tortuosity of the vascular, local vascular system. And more generally, the more tortuous the vessels will be, and the more complex the operation will be. So it's also an important information to take into account. And so overall, knowing a bit more the geometry of the blood vessels that the radiologist will have to tackle with is important for the planning of the operation. And so to make these important choices, the interventional radiologists typically have to read this kind of 3D scans representing the blood vessels in the targeted area. But these images are quite tedious to navigate into and to analyze, especially in some dense areas of the body, like in the brain, where there are many blood vessels everywhere. Actually, the brain area is quite important, clinically speaking, because it's related to stroke management. So our goal is to design basically new visualization techniques in order to help the doctor reading this kind of images that will be quite complementary to what they have currently, and that could still convey the relevant information, in particular the geometric information that they need to take their decisions. So more specifically, our goal is from 3D scans, like we have seen earlier, to output some kind of a 2D representation of the same vascular tree that will preserve the vessel length exactly to still convey the right information about the distance from the source to the target, that will approximate the vessel curvatures as well as possible, that will contain no intersections in order to make the output unambiguous. And finally, we want it to be as easy and simple to read as possible. And one of the inspirations of this work is this kind of vessel maps that were typically obtained decades or centuries ago by performing real dissections on real brains, and that give a sense of what we are actually looking for. And before diving a bit more in the method, I will just say a word about this tree structure hypothesis that I will make through the talk. So actually, the human blood system is not a tree. It contains cycles. And for instance, here in the brain area, we have a quite large cycle called the cycle of Willis located around the neck. So it's technically false to assume that any vascular system will be acyclic. However, it will make the problem of 2D representation way harder to tackle with. And in practice, all our clinical data has a topology of a tree. So it's not a big assumption for these kind of applications, although this is something to keep in mind. So that being said, the problem of representing vascular trees and vascular system in general in a 2D way is not new. And there's a whole taxonomy of methods that have been proposed in the literature, depending on which kind of vessel structure we are working with, depending on the data structure used to encode the blood vessels, and which kind of information we are trying to convey. And here are some examples of what have been proposed so far. And in the vast majority of these cases, the information about the geometry is either absent or encoded in an abstract way. There are actually very few methods that really focus on the geometry and the curvatures of the vessels. And probably one of the reasons for that is that it's actually a quite challenging and ill-posed problem. First, because of course, since we are reducing the dimension, we are losing ultimately geometric information. So we have to make a compromise to define which kind of information we really want to keep and what other, let's say, part of the vascular system we are ready to approximate more. Which requires some effort in the explicitation, the modelization of the problem. Second, since we are designing visualization techniques, the readability of the output is something important, and it's also something that is quite hard to formalize mathematically. And finally, because of these intersection-free constraints, even though we can design some optimization problem, optimization formulation for this problem, it will still be non-convex at the end of the day. So in order to find a satisfying solution, we'll have to rely on heuristics. So for all these reasons, it's quite a hard problem. Now, a natural idea, a natural strategy to try to tackle this is to try to separate the two sets of constraints that make the problem hard, namely the geometric constraints and the intersection-free constraints, and try to handle them separately. This leads to two kind of embedding strategies. The first one consists in first trying to compute the first projection of the 3D vascular tree without taking the intersections into account, and then try to remove the intersections a posteriori. And the second strategy consists in doing things the other way around. First, compute an embedding that is intersection-free without taking the geometry too much into account, and then trying to refine the geometry in a second time. So interestingly, most of the few works related to geometric preserving embedding focus on the first strategy, probably because it's easier to define what is a geometric projection from 3D to 2D, rather than trying to refine it afterwards. And so this is how a typical method of the literature looks like, starting from a 3D tree here. The authors apply some combination of linear projections in order to get a first 2D embedding that may contain intersections. And then by using some kind of a bounding box technique, they adjust the position of each vessel in order to remove the intersection, giving something like this as output. So this first strategy is quite natural because we can perform this first geometric projection using quite a natural projection techniques. However, the main problem is that it doesn't scale well with the number of blood vessels. First, because depending on what technique is used for the second step, it may be impossible to find a configuration, an adjustment of the first embedding that will remove all the intersections. And second, even if a solution exists, moving one branch may create one or several other intersections elsewhere. So this makes the problem quite hard to track computationally. So for these reasons, and since that in our case, our vascular trees are so dense that trying to preserve the geometry quite exactly doesn't make sense, we rather use a second strategy where the intersection-free constraint is satisfied by design, and where we focus on the geometry in a second time by trying to refine a first guess for the planar embedding. So now that we have, let's say, defined our overall strategy, we need to explicit a bit more what kind of geometric constraints we are working with, and what does it mean to preserve the curvatures of the vessels. So first, I will just mention quickly that in general, our inputs, are 3D images on a grid of voxels, and our method rather take three structures as inputs. So there is a word preprocessing step required to extract the tree structure from the raw image. So this necessitates quite advanced segmentation techniques in general, because depending on the quality of the images, trying to have topologically accurate segmentation is quite hard. In general, we'll always have some cycles or disconnected components appearing in the process. And so this is an active area of research. But in our case, our data is sufficiently high resolution for this preprocessing to work with quite simple algorithms. So that being said, I will just assume now that we have already done this first preprocessing step, and that our input takes the form of a tree already.
And say where the data comes from, or to say. No, so just to be clear, because maybe if you're used to seeing MRI or CT scans, the image on the left already seems like it doesn't look like raw data. It already seems to be segmented. But the thing is that when you're working in an interventional context, there are lots of things that you can do that you cannot do usually. So here, to be clear, the images that you're going to see, they are from the Hôpital La Pitié-Salpêtrière, in Paris. And basically what happens is that someone is being, there's an intervention going on the patient, and the patient is completely, they say, pluralized, which means that basically the respiratory motion is artificial. So what they do is that, okay, the patient lies on the table, and you take a first CT scan. So you get an image where you have, for instance, the skull, the bones. Okay, so before taking the image, you you turn off the respiratory system, so the patient lies completely still. Then, okay, you take the image, okay, then you inject a contrast agent, which makes the blood opaque to X-rays. You take a second image, so now you see the skull plus the blood vessels. Then you turn on the respiratory system again. And the idea is that because the patient is completely still, to get the segmentation of the blood vessels, you just need to make a subtraction of the second contrast agent injected volume minus the first one where you only had the skull. So it means that time for free, no deep learning involved, you get this super high resolution image on the left. Okay. But obviously, you know, the long-term plan is to have the visualization method attached to maybe deep learning techniques for more, let's say, mundane image acquisition pipeline.
Mm-hmm. But so here, our method doesn't really deal with this step anyway. So we'll just assume that we already have the topologically accurate segmentation on the right as input. And formally speaking, our input is a rooted tree whose vertices are points in 3 dimensions and corresponding to the voxels of the tree input. And each edge links neighboring pixels so that each blood vessel corresponds to a chain of edges. We also want the tree to be directed in the direction of the blood flow so that the tree root corresponds to the blood influx in our vascular system of interest. So in our case, the root will be this node here on the bottom.
And you can say that, to be clear, what is the picture that we're seeing? Because we are so used to it,
yeah,
that it's a left hemisphere. I don't know if you can see it. Of the carotid arteries.
It's like this part of the brain.
So like eyes are here, okay, to be clear, and that's this artery.
And so this is our tree model in a more visual way. So this is a detail of the input tree. And here the different dots represent the different vertices in 3 dimensions of our input. And the edges follow the blood lines by linking these vertices together. So all these points are in 3 dimensions. And our goal now is to compute a 2D coordinate for each of these vertices, that will define our final embedding. So actually, rather than computing 2D coordinates directly, we rather use a change of variable to make the problem simpler based on the following observation. If you know the embedding of one node, then the embedding of its child, of one of its child, will be entirely determined by the vector going from one node to the other. And if we want to preserve exactly the length of the blood vessels in our embedding, it means that the magnitude of this vector is fixed as well. So the only degree of freedom is the orientation of the vector. And this orientation can be described by a single real parameter, which in our case, we chose to be the angle made by the vector and some arbitrary axis that here is the vertical axis of the embedding plane. So by using this new system of coordinates, we have a simple expression of the embedding of one node given the embedding of its parent, where here the norm, the distance between the 2 vertices is fixed by the 3D input structure. This way, the length reservation constraint is implicitly satisfied. So we are reducing the number of free parameters and removing one set of constraints to deal with. One other advantage of this angular parametrization is that it makes the curvature constraints easier to formulate, because trying to enforce the curvature of the embedding to be equal to the curvature of the input amounts to constrain the angle between two successive edges in the 2D space to be equal to the corresponding angle in the 3D space in absolute term. And this means that we just need to constrain the absolute difference between two angular parameters to be equal to the angle made by the corresponding edges in the original tree. So of course this is not enough, because due to this ambiguity on the sign of the difference, two very different curves may have the same, let's say, absolute angular curvature. And so we need a way to define which sign we are enforcing on the difference as well. And this is a fairly tricky problem, but a natural way of doing so is basically by transporting, let's say, a local frame, local coordinate system continuously along each blood vessel by just choosing a normal of the blood vessel at one of its origin. So basically, it corresponds to choose one sign, one orientation of the normal, because like the normal space of the curve will be a single line. So we have basically two choices for the normal, and then by transporting it continuously along the curve, we'll have, let's say, a notion of local orientation of the normal space that we can use as, let's say, left-right to define in which sense the left or the right the embedding should bend in the 2D space. So mathematically, it just means that we have created a set of normals that move quite smoothly along the blood vessels, and we define the sign of the angular difference to be the sign of the projection of the next edge on the normal of the previous node. So basically, what matters here is that using relatively naive techniques, we are able to define a smooth notion of let's say, absolute curvature, signed curvature based on the absolute curvature we have defined before. And another thing is that this notion of, let's say, continuity of the sign makes sense on continuous vessel, but at junctions we have some kind of discontinuities, so it doesn't really make sense to try to enforce the sign curvature to vary smoothly. And so in practice, rather than trying to rely on the previous technique to define the angle of the curvature at these nodes, we just choose to switch the orientation of the blood vessels at junction nodes so that they follow some kind of global alignment with the original, with respect to the original tree. So basically, we use this additional degree of freedom to ensure that the leftmost vessels on the 2D plane correspond to the front vessels in the brain, and that the rightmost ones correspond to the back of the brain in the original tree. So all these details are fairly technical, but what really matters at the end of the day is that by defining this notion of relative angular curvature, our geometric preserving constraints just write as follow, where this kappa is defined as earlier, and so that the final embedding position of each node can be obtained through this simple formula. And now, if we replace this approximation here by a strict equality, we obtain something like here on the right, that clearly contains too much intersections to be handled afterwards. So now we need to find a way to obtain a correct intersection-free embedding of this tree structure by playing on the approximation here, so that we obtain something that we can actually work with. So now, in order to get the first intersection-free layout that is minimally geometrically informed, I will just recall that the main problem, the main difficulty of all these intersection-free geometric preserving problem is related to the scale of the problem. That if we have to handle too much vascular, too much blood vessels, then the problem becomes basically intractable. But in this kind of problem, where the scalability is the main issue, and especially when working with tree data structure, natural strategy is to rely on recursive algorithms, in which we'll decompose the original problem into several sub-problems of smaller scale that we can just solve independently and then combine the solution in order to get a solution of the final problem. And this kind of strategy is especially suited here because although our full tree contains thousands of nodes, most of them doesn't really contain any topological information, and only hundreds of them are actually located at a branch of the tree. So the vast majority of the vertices we have only have one child, and so we can kind of condensate them to construct a coarse tree structure that completely describes the topology of the original one, just with a few hundreds of nodes. So more specifically, from our original tree, we build a coarse one whose vertices correspond to the junctions of the original tree that I depicted in blue here, and whose edges correspond to each single blood vessel. And by applying the recursive algorithm on this coarse tree, we are able to design a recursive procedure that actually scale with a number of branches. Now, one last thing that we have to take into account is that in order for the recursive algorithm to work well, we need to be able to just create a solution of the large-scale problem from solutions of the smaller-scale problems. And if we do it naively, basically the solution of the sub-problems may just overlap if we just put them together. So in order to avoid that, we'll rely on a tessellation method, where we'll just split the embedding space in a small subspace in which that will partition the original space, and in which we'll force the sub-trees to be contained in. So in this way, we can just build a solution of the full problem by just appending the solution of the small problems. And because of these bounding constraints, we ensure that each individual subtree will not overlap with the neighboring subtrees. So algorithmically, this is how it works. Starting from a bounding box that corresponds to the whole half plane, we will process each junction node of the course tree as follows. So we'll just embed the few branches directly emanating from the current junction node using, let's say, brute force techniques that that can work well when the number of branches is moderate, and so for which the scalability is not a problem. Once we embedded the first generation of branches, we'll split the remaining of the current bounding box into new several boxes that partition the space, and in which the next subtree will be constrained as well. And so if we make sure that these branches do not overlap together and remain correctly in the box, this ensures that we can just embed the next generation of subtrees independently without looking at what is happening elsewhere, and still ensuring that everything will be intersection free at the end. So in order to make it more visual, I got a small animation of what is happening actually. So we see that at each step of the algorithm, one new junction node is processed, and during the processing, one level of branches is embedded, and the remaining of the space is split. And by ensuring that the different splits don't overlap, we make sure that the final algorithm, the final embedding, is intersection free. And so you can see some boxes making weird stuff. This is because in practice, we have some additional trick to optimize the use of the space to avoid that everything gets shrunk too quickly. But basically, from this, we obtain a first embedding that is guaranteed to contain no intersection, and that contain a bit of geometric information, but clearly the result is not satisfying. In particular, the extremities of the tree are quite stretched, and so this is clearly not suitable for visualization purpose. So now we go to the second phase, where we'll improve the geometry of this original tree.
One question. What were the red dots? And the red dots?
This one?
Yeah.
These are the nodes just before an intersection, either with a box or with another branch.
Oh, that forced you to...
Yeah. So basically, once we detect a collision, we'll just follow, let's say, a straight line, or interpolate between the original branch and straight line to ensure that no collision will occur anymore.
So maybe a remark, I don't know if we're going to discuss it at the end, but I think what's really interesting in this field is that depending on the intervention that you're making, you're going to prioritize or preserve some aspects of the 3D geometry into the 2D visualization. So for instance, Guillaume briefly showed visualization that are tailored for interventions with needles. But here the point is that it's tailored for interventions with catheter, like endovascular intervention. So basically, you know that you cannot fully preserve the curvature and length. Because if you think about a helix, for instance, a helix, you cannot embed it in the plane without intersection, you run into trouble. So here the kind of assumption is that what is most important is what happens just after a branch. Because basically, you know, with your tip, once you have inserted your catheter inside the vessel, that probably you can push and it's going to be okay. But you know, the better you preserve what happens right after node V, the better. So I think that was
yeah. Basically by using a technique where we try to fairly preserve the branchings close to the junction node, we ensure that things are quite well preserved around the branch, that we have rather accurate angles at intersections, and it also gives, let's say, a distance or a number of nodes around the junction in which we are sure to have an embedding that is locally intersection free. So somehow it gives us a notion of the scale at which we can just have an accurate preservation of the vessels. So that in the second step, we can just, let's say, rigidify this part, leave it untouched, and ensure that the angles are well preserved, even though we may change all the location of the nodes that are located further on the branch. So maybe it will be clearer after I explain what's happening in the second step. So basically, we are using a typical classical technique for graph visualization called force-directed algorithm. The idea is to adjust iteratively the position of the nodes, or in our case, angular parameters, by applying a set of forces to them that will enforce them to follow the desired properties. So in our case, there's one force that we try to push the nodes from each other in order to make them occupy as much space as possible and avoid intersections. One term that is more here to enforce a bit more the curvature constraints, and the last one that is more here for stability reasons. So the first term takes this form. It is quite complicated, but basically this is just some, let's say, gravitational repulsion force and some electrostatic repulsion forces that are multiplied by a term that keeps the scale local and make sure that thing does not like the influence of very far away nodes does not interfere with the local scale. The bending constraint just try to enforce the sign curvature constraint with a coefficient that depends on the local radius of the blood vessels to prioritize the larger vessels. And the last term tends to push the current embedding towards the original one that we computed before to make things a bit more, let's say, convex and stable, so that the thing really converge to something. But so this part is quite, let's say, manual somehow.
It's out there. Like in computer graphics, you say, okay, as an artist, you can decide how the visualization is going to look like.
It's basically a try and retry, and then this is how it looks like dynamically. So starting from the original tree things get pushed to spread within the space and try to make the curvature a bit more faithful. And we have these small effects here that are just because in practice I crop the gradient when it becomes too large. So it makes things shake a bit. But at the end we still obtain something that works well for our needs. And that at the end of the day, from this 3D structure, we obtain something looking like this, that correspond to what we are actually looking for. So even though it's hard to quantify and to know if the intrinsic geometry of the tree is well preserved, at least we have something that still conveys some geometric information while being quite easy to read. And for instance, we clearly see the aneurysm here on the 2D representation, which is quite hard to read on this image. So we have it here. So of course, by turning around, we will see it clearer, but the point is that having a 2D representation makes things way more visual. And so here are some other examples that we computed. So the first example that I showed before was a pretty large scale one in order to assess the scalability of the method and to better visualize what's going on. But for clinical purposes, we are actually interested in a smaller part of the whole brain system because the targeted locations are way closer to the origin than what was shown before. So we can just restrict a bit more which part of the brain we are working with, and which makes the visualization more accurate in terms of curvatures because we have less branches to stack on the embedding plane. And so from this 3D tree, we obtain some 2D representation here where we can represent the surgical route to the aneurysm, and we can encode some information related to the curvature, for instance, here. And we see that let's say the curvature of the path seems fairly accurately depicted in the results. So it seems quite, let's say, satisfying. Yeah.
I don't know if you're going to say, but Tom Boken, probably if his children were not sick currently, he would have been able to come and say why this is actually clinically relevant. So I don't know if you're going to say it. No? Okay, because basically when you see it, you may think, okay, it's fancy, but who cares? But the thing is that when you start talking to people who do surgery, who do interventions, etc., they always talk about the gut feeling and the experience, right? So basically what they call gut feeling is the difference between what you can teach to students and what you do after a decade of practice. And basically for this specific problem, the experience and the gut feeling is important when they when they see the 3D volume and they decide, okay, what are the catheters that I'm going to choose to reach this location? And basically, a young radiologist would maybe pick a catheter, try to insert it, but it does not have the correct flexibility, the correct bending properties, and basically is not able to reach the aneurysm, so you have to take it back, and then you need another one, and basically you wait quite a lot of time, so you waste a bit of money. Like I think each catheter is on the order of 500 euros or something, but most importantly, those kind of interventions, they are super dangerous, actually. Like I think you have a 1 in 10 chance of dying, or something like that. So it's a real dilemma actually for them to decide whether or not they are going to operate those aneurysms. Typically, aneurysms like this, they are detected by chance. Someone going into an MRI scan for another reason, and then the radiologist tells you, oh, we have very bad news. There is an aneurysm in your brain. Then, okay, they decide maybe it's worth it to roll the dice. But you imagine that when you have those very high-risk interventions, you'd be happier if you could succeed on the first try all the time. And that's basically what those visualizations are there for. It's to try to let young or not very well-trained radiologists very quickly assess how difficult the path is going to be, and therefore hopefully pick the correct set of tools.
So they have 3D visualization, like
no, so they see it on the screen.
just the screen.
Yes. So also, I think we also talk to surgeons, to orthopedic surgeons with other projects. I think they are the one population that I know of who are really fond of VR, of virtual reality, because for them, the main appeal of VR headset is that you don't have a screen encumbering. Basically, you don't need a screen on top of the patient that you are currently operating.
But it's not right now, but the research is
Yes. Basically, you have people using it like a gadget and trying it,
okay.
but at least with our colleagues, it's not used routinely.
Maybe just to add a quick point, we are working at with the cardiac surgeon that operates the coronary arteries on the heart, and he's very fond of VR and using it to teach to his students. He's called at the hospital bishop.
Okay, it's current.
So it's kind of a niche. Like some people are starting to love it and use it, but it's not kind of clinical.
Okay.
And I don't know if you're going to talk about run times.
Oh, no, I didn't. But yeah, basically, the big example I showed before, the embedding part takes a few seconds, like maybe 3 to 5 seconds, depending on whether we use GPU or CPU. But so this is a magnitude of order, and this is a smaller example. So yeah, it's like a couple of seconds to compute that.
And on the raw data we showed you, even the pre-processing is very fast. And that was really a big constraint for us, is because we work in this clinical environment. You want something that runs in a few seconds on a normal laptop. Otherwise, there's absolutely no chance it's ever going to be used in clinical practice. So.
Then they do the visualization like this, and then they choose the catheter, and they flow it by imaging.
Yes. Yeah, exactly. So the whole game in those kind of interventional techniques is that usually you have a 3D scan, but usually you cannot operate with real-time 3D. So usually it's more you have 3D, and in real time you have a 2D view. And so you have to imagine in your head, like, okay, how does it work, etc. So it's really quite complex. I think the best comparison is taxi drivers in London. Like 20 years ago, there were studies and they showed, they have a huge cortex for location or something like that. So it's doable, but very hard to scale to a full country. And hopefully with those techniques, which are a bit more like Google Maps, you'll be able to democratize those techniques.
Can you follow? So on time, do you put the catheter on your 2D projection? Or?
No. So far we haven't done it. So, and to be clear, this is very, very recent. So it has not been used actually live by our colleagues. But I think Guillaume is going to show you the other applications more for research, which are
It's not here. But basically, the 2D coordinates here are just some features of each vertex here. So if we have a way to track things on the 3D tree, then we can just transcribe it on the 2D projection as well very easily. And so similarly, everything that we can represent here can be represented here directly without any overhead. And so there was an example, like surgical planning example, but we also tried some method on different other things. So here are some other brain. I think of fetus. Okay, no fetus.
No, this is still la vitesse salpêtrière.
Okay. So still the same, but where we colored the different areas of the brain to see how it differs from one image to the other. And since we aligned the branches in a globally meaningful way, we have these nice clusters represented here that are consistent from one view to the other. So we may use this kind of visualization to compare different brains as well, trying to, I don't know, to explore a bit more the structure of the brains of different persons in a more easier and more visual way. And we also tried the same method on other parts of the body, like here on the knee, where we segmented the artery around the bone, and we embedded with our method, which also gives, let's say, coherent results. And similarly for the pelvic region, where we get something that really helps to visualize the whole structure of the vascular system there. So overall, our method provides a new way to visualize vascular tree that scale well to large blood systems and that give fairly satisfying results. There are still some limitations to address, notably the sensibility with respect to the choice of parameters. We've seen that in the force-directed steps, there are many parameters to tune. It's not very obvious how to choose these parameters correctly, and from one input to the other, the right set of parameters may differ quite a lot. Similarly, other recursive technique is based on some brute force strategy to embed the different branches, but a small variation in the original tree may lead to quite different results overall. So this is something that we'll have to investigate as well. And there are some artifacts that I haven't mentioned yet, but for instance here, where the bending is not natural compared to the original one, and this kind of thing, like these small bumps, whereas we will expect something smoother, is mostly related to the estimation of the curvatures locally, because the formula that I've used is quite naive, but in practice, since we are computing tangents, normals, and so on, we are relying on, let's say, first-order quantities that are quite noisy. We see here that the segmentation is a bit shaky, and so this biases the curvature constraints that we are enforcing. So there's still some work to do on that part, on how to compute curvatures in a more robust way. So that's it for the work. We have published it in MICI of this year, so we can check. You can check the article if you're interested. And of course, if you have any question, I can answer now. So, thank you.
And so you mentioned it in the conclusion, but like for the choice of the parameters, for example, do you rely on metrics or stuff like this to choose them, or because you discuss the results more visually?
Yeah,
But I bet you're not only.
well, I relied on the guts, basically. But no, it's mostly for what seems the most correct visually speaking.
Okay.
So basically, the thing is that when you have trees that have roughly the same shape, the same number of nodes, and so on, things the same set of parameters is quite adapted from one to the other. The problem here is that if you have a large tree and a smaller one, like with less resolution, for instance, or less nodes, then let's say basically these parameters are not invariant by rescaling, something like this. So when you change the scale, you need to change the parameters adequately. And so I haven't thought about a natural way of doing that automatically. So I need to adjust everything at each time. And yeah, when the curvatures are larger, maybe you need to weight less the curvature term in order to make things more stable, those kind of things. So yeah, this is something to look more into. But,
And maybe a remark is that so you said that going forward, you'll have one work in progress is to see whether or not it could actually be used in a clinical environment, but also the whole thing about making large-scale visualizations in a population, trying to understand what are the blood vessels which are reproducible between patients and for which structures you actually see a lot of variability. This is really the type of questions that interventional radiologists or surgeons are interested in. I think the main shock for me talking with those people is how little is known, actually, even on our bodies, because, for instance, the blood vessels, they were not deemed super important until very recently, because the small blood vessels, when you cut them from the outside, who cares? But now that they are used as highways to reach different parts of the body, then suddenly, so for instance, when you talk to, I don't know, Tom or other people, they tell you, oh, we discovered an artery somewhere around the pelvis, for instance. You're like, what does it mean, discover? No, that's really how it works. And so the good thing is that Guillaume obviously worked a lot on the software side, like a very good implementation, very fast and fairly portable. So the code is available online. It's actually in a folder of circuit shapes. And even the people at General Electric, so that's the team where Pierre-Louis Anton-Santi did his PhD, if you remember him, he continuously contacted us to say, oh, it looks good and our data, etc. Would you like to discuss it with us? So I think it's also the good thing about high quality open source software development is that people spontaneously